Okay, so welcome to the second part, second part in terms of the major solution procedure of the torsion of a non-circular cylinder problem. So last time we discussed essentially the displacement-based approach. We have the cylinder with a non-circular cross-section. Any cross-section area, remember, is S. Boundary is denoted with del S. And we introduce the arc length parameterization around the boundary indicated with small coordinate, small letter S. And we impose either a torque or an end twist beta. And alpha eventually is the twist per unit length, which is beta over the length L. Okay? And we discussed the mechanics of the problem. I did a small experiment on our sponge. And essentially, we observed and argued that the in-plane displacements, the displacements within the plane of the cross-section, it's along x1 and x2, they retain the form that we already knew from our torsion of a cylindrical cross-section problem. So that is that form. Remember, there's the assumption that the rotation is small. That is invoked. That's always there. So that's that form. There's nothing new about that. But then we observe that there is an out-of-plane distortion of the cross-section. It does not remain as a plane after torsion. And we argued that that is proportional not to the absolute twist. We observed that, for instance, even if one end is not twisting, the amount of distortion is the same irrespective of where I am along the axis of the cylinder. And therefore, what should be characterizing the extent of distortion should be alpha. And it should somehow be proportional also to a quantity that depends, arbitrarily complex at this stage. We don't know what it is, but some function of x1 and x2 because the distortion is not uniform on the cross-section. So that is a fairly general and reasonable assumption to make as a problem-tailored form for our displacement, right? And then we proceeded with the first, this is the displacement-based approach. We proceeded with the next steps of the displacement-based approach. So notice, as I noted last time, and as we will also see for part 2 on the stress-based solution approach, the arguments and the steps are the same, but it's not entirely the same as before in the problems that we considered in the displacement-based setting because we introduced not only a simplification of the displacement based on the, let's say, cylindrical or spherical symmetry, we actually introduce a function that says something about the displacement. We do something extra in some sense. And in this problem, there is absolutely no symmetry anyway. So we are stuck in Cartesian coordinates. So it retains the major steps of the displacement-based solution approach, but there are some clever steps that are taken. So then the general steps are strain to stress, and that's the form of the stress. And then that has to satisfy equilibrium. And we found that satisfying equilibrium is equivalent to saying that Laplacian of C is equal to 0. Okay, that's straightforward. And then we talked about the boundary conditions. There are two sets of boundary conditions. One, on the end where I impose the torque, the stress distribution has to be statically equivalent to simply a torque. Okay? And we showed that the forces identically vanished within our construction of the displacement field. I don't have to worry about them. Moment about x1 and x2, they identically vanish because sigma 33 is 0. And the torque eventually is given by, or it's related to the twist per unit length through this expression where J tilde, we called it the torsion constant. It's almost the polar moment of inertia, but deviates from it through the presence of psi. Okay? Because this is not a circular cross-section. If the circular cross-section is invoked, then J tilde is equal to the polar moment of inertia. Okay? But there was another condition which said that these lateral surfaces are traction-free. I'm not doing anything there. And that traction-free condition is a little bit nasty, the way it looks. And this is the way we have derived it. And that's certainly also something that we need to satisfy as we try to find what this particular function psi is, which, remember, we call the warping function. So that's where we are. And that's what we have completed in the first part. Now, let me move to the second part. And eventually, here I will write the major observations from that part of the solution, the second approach, which is now what I'm going to discuss. So part 2 is stress-based solution. Now, just like in the first part for the displacement-based approach. This part is also going to deviate immediately from the outset, actually, from the earlier stress-based approaches that were exclusively based on the area stress function. Now, remember, when we were constructing the area stress function, we constructed it for intrinsically two-dimensional problems. So they had to be plane stress or plane strain. This problem is not plane stress, it's not plane strain, it's a fully 3D problem that I have to consider. Okay? So the approach is going to be stress-based, and I'm going to follow the major ideas of a stress-based solution approach, but obviously I cannot use the area stress function because of the fact that it is not a intrinsically 2D problem. So, nevertheless, we are going to proceed with the observations or the expectations. Now, I already have written what the form of the stress is. Now, you can either motivate yourselves based on that, or you can just look at the problem. Well, I'm putting a torsion, so I'm not pulling on it. I don't expect sigma 3,3. There can at most be sigma 3,1 and 3,2. One way or the other, you argue that eventually, in this problem, the only stresses that I will have are sigma 3,1 and sigma 3,2. That is the starting point for a stress-based solution approach. That's observation number one, right? So what we are trying to do is we're trying to construct again, a problem-tailored form, if you like, of the solution. Okay. Now, we are going to assume, okay, and it turns out it's a very good assumption, and it works, that the stresses are derivable from a certain function, just like in the area stress function approach. But in this case, I'm going to call the function phi again, but the relation between the stresses and that function, if you will compare, they are different. So this is what we are going to propose. Now, we are assuming at this stage, but it turns out that assumption, just like in the case of the area stress function, it's a reasonable assumption. And eventually, this approach that works is based on what is called the Prandtl stress function. Okay, so, well, now, what do I mean by the fact that the major steps, again, of a stress-based approach are retained? What I mean is you proceed with the usual steps as we did when we were driving the area stress function approach. What we did, so by the way, please don't be misled, right, by the choice of the notation. So before, in the area stress function-based approach, we had both a phi and a psi. So now that phi and psi, they take different meanings, but I think the context makes it fairly clear. What we have to do now is, okay, well, we have a stress field, and the idea is to sort of go backwards towards the, eventually to the displacements, right? But that loop, as we argued in the area stress function-based approach, does not pass through the equilibrium requirement, and therefore it has to be satisfied from the outset. Let's see if it is. Okay, so equilibrium is something I have to worry about, but it's automatically satisfied, it turns out. And that is precisely why, in fact, you choose such an assumption for the form of the stress. So equilibrium in this case, we've already discussed it in the first part. It simply has to do with the, along the x3 coordinates, sigma 3, 1, comma 1 plus sigma 3, 2, comma 2. Has to be equal to 0. Sigma 3, 1, comma 1 is phi, comma 2, 1. 3, 2, comma 2 is minus phi, comma 1, 2. And therefore, the result is 0. OK, good. Now, Then the usual step, of course, right? The idea is to somehow construct now a problem-tailored form for phi, invoke boundary conditions, etc., and determine everything that has to do with phi. But eventually, I'd like to be able to construct the displacements out of it. And remember, therefore, I need to make sure that compatibility is satisfied so that there is actually a displacement field, physical one, that is associated with the stress field. And therefore, as we did for the stress-based solution approach, we have to satisfy compatibility. Let me discuss this separately over here. So we must ensure compatibility with the presence of a physical displacement field. So presently, right, stress is equal to lambda epsilon v, but volumetric strain will be 0 in this problem. It is 0. We've already discussed it. So stress is simply 2 mu epsilon, right? And therefore, epsilon is 1 over 2 sigma, and therefore epsilon will have the same form. I don't know what the components are presently. All I know is that only 3,1 and 3,2 components, and it's symmetric, are quantities I have to worry about. And moreover, actually maybe I should make a note of it here as well. I expect these to be functions of x1 and x2 only because I'm working on a plane on the cross-section. The distribution is going to be over the cross-section. I don't expect any dependence on x3. So likewise here, I expect dependence, therefore, based on the stress observation, only on x1 and x2. So that being the case, at this stage, what you can do is you can look at the 6 compatibility equations that we had introduced way back at the beginning of the course. There were 6 of them, and it's a fully 3D problem. You have to look at all 6 of them. And among those, only 2 will survive because of the fact that only these are non-zero and they do not depend on x3. And those 2, let me remind you what they are. So only 2 equations out of 6 survive. And they are minus epsilon 3,2, comma 1, 1, epsilon 3,1, comma 2, 1, and another one. Okay, so those are the 2 compatibility equations that I need to worry about. Now, stress is 2 mu epsilon. Since I'm working in terms of stress, we did this rigorously, took some time in the area stress function. Here, I'm doing it on the fly because it's quick. So I want to work eventually in terms of stress, so I need to convert this relation to stress. But here, because of this simple relation, because volumetric strain is 0, I can do that immediately. So in terms of stress, what I need to satisfy is 0 is equal to, the first one is simply going to be, just replace epsilon with sigma. I'm getting rid of or multiplying both by 2 mu, if you like, plus sigma 3,1, 2, 1. And 0 is equal to minus sigma 3,2, comma 1, 2, plus sigma 3,1, comma 2, 2. Okay, so now we do know that sigma 3,1 is phi, comma 2, right? Let me just make a note of it on this board, just for this part. It's phi, comma 2, and this is minus phi, comma 1. And likewise over here, right? So I'm just going to make that substitution. So here I will have phi, comma 1, 1, 1, right? There are 2 1s here. And then here plus phi, comma 2, 2, 1. And then this one becomes minus, minus again, phi, comma 1, 1, 2, plus phi, comma 2, 2, 2. So I look at this quantity. I see comma 1, 1, 1, 2, 2, 1. So this is phi comma 1, 1 plus comma 2, 2, comma 1, right? And that is nothing but Laplacian of phi comma 1. And likewise, if you look here, 1, 1, 2, 2, 2 is present in both. This is nothing but Laplacian of phi comma 2, right? So Laplacian of phi comma 1 and comma 2, they are both eventually 0 because of the compatibility requirement, which says that Laplacian of phi is at most a constant. For every point on the cross-section. So now this is our requirement. In the area stress function-based approach, there was a similar requirement on the area stress function. And in this case, it's actually simpler. There is a disturbing point at this stage. Eventually, this equation will be made use of while I'm trying to determine phi. But at this stage, if I don't know what that constant is, I cannot solve that equation, right? So that's what's disturbing. So eventually, I will show you in about 10, 15 minutes that this constant is actually equal to minus 2 mu alpha, right? 2 is per unit length, shear modulus, etc. So I know actually what that constant is, okay? But at this stage, it's not clear. So that is the compatibility requirement. Now, equilibrium is satisfied from the outset. I don't have to worry about it. Compatibility is now what I have to worry about. That's the major difference, right, between stress and displacement-based approach. The rest is similar. I have to satisfy boundary conditions. So let's have a look at boundary conditions. So the first thing I will look at is the traction-free boundary condition. So del S is traction-free. And now, at this point, I'm just going to borrow the relation that I developed last time, or we argued. We said that the traction on del S, okay, it's equal to, actually, the traction on S is equal to sigma times any normal, but on del S, that normal is m, and therefore the traction on del S is sigma m, and that has to be equal to 0 because it's traction-free, right? And we have derived what that equation entails, and it condenses down to what we called double star. So I'm just writing this equation double star from the displacement-based approach that we considered last time. And that is equivalent to, okay, sigma 3, 1. So this is nothing but sigma 3 components multiplying the normal to the boundary. And that normal has components dx2 ds and minus dx1 ds. Okay, so sigma 3, 1 is equal to phi comma 2. I'm just substituting dx2 ds. And sigma 3, 2 is minus phi comma 1, another minus, so it's ds. So phi is a function that depends on the coordinates of the boundary. You can write those coordinates either in terms of x1 and x2 or in terms of s. With s, there is only a single coordinate that traverses the boundary. If you write it in x1 and x2 and then you want to take a total derivative with respect to s, you go phi comma 2, 2 with respect to s, comma 1, 1 with respect to s. But that is nothing but d phi ds. It is the total derivative with respect to s. Now, the total derivative with respect to s equals 0 means that phi is a constant on del S. Right. So it's a very simple result. Now, we don't know what that constant is either, okay? But eventually, what I do know is that, and what we will observe together once again, is that it does not influence the stress, because the stresses take derivatives with respect to 1 or 2, and that constant will vanish eventually anyway. So if I just change this constant, the value of phi everywhere will shift by that amount, right? The value that I pick here will eventually have a tiny implication on the calculations that I make, but it's very clear, right? So what I'm going to do is I'm going to pick this constant to be 0. This is our choice. It doesn't have to be 0. You can pick it to be anything, and it's absolutely arbitrary. Okay? But if you pick it to be 0, some relations, I'll tell you which one in particular, is going to simplify. Now, therefore, right, we argued that, okay, eventually you choose a displacement or a stress-based approach for a certain reason. So, for instance, at this stage, we could say that the stress-based approach is advantageous in the sense that, so I need to pull up a board over here. In the displacement-based approach, I have to worry with this condition that satisfies or enforces traction-free condition. It doesn't look so simple. Now, the first one is very simple. So now when I move to the stress-based approach, the equilibrium is satisfied by compatibility. It's a very similar condition. It's not really any harder or easier. But the traction-free condition has become exceedingly simple to satisfy. In fact, I satisfy it from the outset, if you like. Right? You could say that this is one advantage in this case of the stress-based approach. It certainly makes the formulation a bit more compact. So we're done, actually, with the stress-based approach, the major part of it. So let me just give you a status update at this stage. We want to calculate the stresses from the Prandtl stress function. The Prandtl stress function ensures that the equilibrium is satisfied from the outset, but you have to ensure that you satisfy compatibility, and that eventually goes as such a requirement. And eventually, on the boundary, traction-free condition has to be satisfied. And we do that by simply choosing phi to be a constant, in particular, 0. Okay? So that is our stage of development. One tiny remark. Eventually, we'll have to solve this differential equation. It's a partial differential equation. But even in that case, eventually, phi could have both a homogeneous and a particular solution, right? The homogeneous solution is Laplacian phi equals 0, or equation is that. But it turns out Laplacian phi equals 0, with phi being 0 on the boundary, can only be satisfied by a function that is identically 0 everywhere. So in this particular case, the homogeneous solution is something I don't have to worry about. I only need to worry about the particular solution, which is this solution. So I'll just eventually attack that one. Okay? Tiny remark in relation to the many ODEs that we solved before. Okay, so now I have not shown you yet the relation of the Prandtl stress function to displacement. Eventually, we'd like to construct that in a stress-based approach. And I still have not shown you static equivalence at the end where we impose a torque. So let me quickly cover those as well. There really is no complication on that part. So I will erase this part. Do you have questions at this stage? Now, also note that this problem is worth sort of covering in, let's say, in such a unique setting, because although I'm solving a single problem, right, in some sense, torsion of a non-circular cross-section, that cross-section is arbitrary. So every time you change the cross-section, it's a new problem. And depending on the complexity of the cross-section, it can be a challenging problem. Okay? So as soon as I finish this, I'm going to solve one example, the elliptical cross-section. And then in the homework, you'll consider a square and a triangular, equilateral triangle cross-section. Those are fairly easy cross-sections to deal with. Okay, so static equivalence at x3 equals L. Now, I had already discussed last time that some of these conditions are identically satisfy. So for instance, sigma 33 is already 0 from the outset based on our form of the stress. So F33 is automatically 0, and therefore M1 and M2 are 0. I don't have to worry about those because sigma 33 is 0. What I have to worry about is F1, F2, and M3, which is the torque. Okay? So F1 is sigma 31 dA. Now, the argument is even simpler than last time, actually. So phi 31 is equal to phi comma 2. Now, I see a function derivative with respect to 2 over a domain. It's a 2D domain. So it's almost like a divergence theorem. It's not, but it's closely related to it. So I already told you, I'm just going to say based on the divergence theorem. The idea is you convert to a boundary integral. You take phi as it is. And instead of comma 2, you take the corresponding normal to that boundary, which is M2. Okay? And we're integrating over the boundary. It's a ds. That is the transition. So now, at this stage, you can already say, based on our choice, we chose, due to the fact that it's a traction-free boundary, we chose phi to be 0. But somebody else could have chosen it to be something else, right? So I'm not going to assume that phi is equal to 0 at this stage. Let me write this a bit more compactly so I can finish in one line. So it's del S phi M2 ds. It could have been any constant. So first, I'm going to take that constant outside, not necessarily 0. For us, it is, but in general, not. And then I'm going to write what M2 is. M2 is minus dx1 ds. Integral, so it's you traverse the whole boundary in the integral, dx1 ds ds, so that's dx1. So integral is x1 evaluated over the boundary. But you start from the same point, come back to the same point, so the integral is 0. Okay? So it's quite straightforward. Okay, so therefore, f1 equals 0 is automatically satisfied, just like it should be. I don't have to really worry about it. And similarly, you can go to F2. F2 is going to be sigma 32 dA. It's going to be S minus phi comma 1 dA. And that's going to be minus del S phi M1 ds. And it will also be 0 by exactly the same type of argument. So that's a clean setup. All right, so now let's have a look at moment about the x3 axis. That one is not going to vanish. It has to be equal to the torque that we impose. And I'd like to express the torque in terms of the Airy's stress function. I'm sorry, the Prandtl stress function. Okay, so the torque is M3, and I already wrote the expression last time and discussed it. So it's simply going to be x1 sigma 32 and a minus x2 sigma 31 dA. I plug in the forms of, so I'm repeating the same thing sort of again and again, the steps. First, I write the expression in terms of stress, and then I plug in the form of the stress in terms of the stress function. So in this case, it's S x1 minus phi comma 1. So I will take the minus outside. There's another one over there. So x1 phi comma 1 plus x2 phi comma 2. Okay, and dA. Okay. So now what I'd like to do is a trick that will simplify our life. This is x1 phi comma 1. I'd like to write it as x1 phi comma 1. But when I carry that relation, I will get x1 phi comma 1, but another term as well, simply phi, right? So for it to be equivalent, I need to subtract that term, so minus phi. Likewise here, I would like to write x2 phi comma 2, but then I will get an extra phi, so I'd like to subtract that. Okay? I've just done a small rearrangement, re-representation of the same quantity. Now, moreover, this is x1 phi, this is x2 phi. I like to call them the components of a vector v, just over here, okay, to simplify things. And now, the reason I do that is because now I clearly see this is v1 comma 1, and this is v2 comma 2. So that's the divergence of the vector that lives in the x1, x2 plane. So therefore, this whole thing is equal to, right, minus minus integral over s divergence of v dA, and then a minus, another minus, and I have two of them, plus 2 integral over s phi dA. Phi is only 0 on the boundary. Inside, of course, it's not 0. Now, divergence of a vector, right, in 2D, based on the divergence theorem, this is del s v dot m dA. Okay? Now, v, I just defined it up there. Let me remind you what it is. Vi is equal to xi times phi. I'm sorry, this has to be a boundary integral s. Right? Divergence, and then v dot m evaluates on the boundary, but v is equal to my choice. It's equal to 0 on the boundary. That was my choice for satisfying a traction-free condition. In general, it's a constant. So if it's a constant, you have to retain this integral. But in my choice, it is equal to 0 on s. Okay? And therefore, from this, I find that t is equal to simply 2. In fact, let's write this separately. We find this very simple relation. Okay. It does require that phi is equal to 0. If it's a constant, you have a non-zero constant, you have an additional term. Okay, so that's quite clean. So as soon as I solve for the Prandtl stress function, I satisfy everything, the boundary conditions, and if I want to process the torque, this is how I process the torque. In particular, if the torque is prescribed, certain constants in it, a constant perhaps, and I can determine that constant by relating it to the torque that I apply. Okay? Or vice versa. If I know everything about phi, then I can determine what the torque is. Okay? That's what this equation serves as a purpose. Now, we want to also relate it to an equation that I have actually written over here. So in this board, you have alpha equals t over mu j tilde, right? So you can work with this equation. And since alpha is equal to t over mu j tilde, you can replace sort of t with it, and you can say that j tilde is equal to 2 over mu alpha integral phi dA. Okay, so j tilde is t over mu alpha. J tilde is t over mu alpha. So if you want to also extract that quantity, the torsion constant, from the Prandtl stress function, also you can do that. Okay? And in this way, relate your stress-based solution to the displacement-based solution. Okay, so there is only one piece of information remaining. Suppose I determine everything, right? I solve the problem. what are the displacements, right? Now, the displacements, again, as soon as you want to construct the displacements, you have to go back and you have to say, well, what is the form of the displacement? So you have to have the insight. You have to be able to say that, okay, U1, U2 are going to take the form from the circular cross-section solution, and U3 has to do with a warping function. You have to have that insight, and then you can use the Prandtl stress function solution to construct what the warping is. Okay? So the stress and displacement-based solutions are not entirely independent from each other because of the unique structure of the problem. Again, it's because primarily because the displacement field has to be sort of reasoned into a particular convenient form. But let's do that. As soon as we have that insight, we can go ahead with that calculation. So to solve for the displacements, what I will do is I will just, right? So we have to first remember that this is the form we are dealing with. And, well, the first two don't really bother me. I need to worry about the last one, okay? That is what I need to construct. I need to construct psi. That's what I need to know. Alpha is straightforward. Let's write the stresses once again, one final time. So sigma 3, 1. I'll write it in two ways. First, the stress-based approach. It's phi, 2 minus phi, 1. And now we link the two approaches. Now the displacement-based approach. It's mu alpha, psi, 1 minus x2, psi, 2 plus x1. Okay. And you go ahead, solve for psi in terms of phi, involving derivatives, of course. So psi, 1 is equal to 1 over mu alpha, phi, 2 plus x2, and psi, 2 is equal to minus 1 over mu alpha, phi, 1 minus x1. And if you recall the procedure that we used to take in the area stress function-based approach, now you have a relation for the displacements in terms of some functions that you partially have to carry out integration on. So in this case as well, I know the relation between psi and phi. In the stress-based approach, I solve for phi. At this stage, I know what it is, right? So I plug it in here. I get a equation for phi, 1 and for phi, 2. I have to integrate them separately, match them, and work out the particular form of psi. So we can integrate towards psi, these two equations. So essentially, this is sufficient to find the warping. And once you find the warping, you're done with the solution. Now, there is one thing that remains. If the amount of twist per unit length is given, right, you will see shortly this solution is one way. If the torque is given, I propose a form for the Prandtl stress function. Using that equation, you determine the complete Prandtl stress function. T is equal to 2 integral of phi. It has no constants anymore in it. But now you might ask, if the torque is prescribed, how do I calculate, for instance, the twist per unit length out of it? Okay, right? Well, you can do it in, well, if you go again to this equation, you can't really use the relation alpha is T over mu J, whatever, J tilde, because J tilde requires that you know what alpha is. So I need to be able to determine alpha if phi is completely null. And actually, so far, if you look back again, there is nothing that tells me what phi is, alpha is, even if I know what phi is. But it's actually hidden in these equations. And let me just quickly show you. And what I'm going to do is, I'm going to take the derivative of this one, okay, with respect to 1. So psi comma 1, 1. And then the I'm going to take the derivative of the first one with respect to 2, and the second one with respect to 1. And I'm going to subtract them. And of course, it's equal to 0. And that is equal to 1 over mu alpha phi comma 2, 2 plus phi comma 1, 1. I'm sorry, plus x2 comma 2, and then minus minus plus x1 comma 1, so plus a 2 there. Okay, so the whole thing is equal to 0, right? And I again revise. I am sorry for doing 2 mistakes in a row. The parentheses should be here. Okay, but that is now certainly equal to 0. So this one is equal to Laplacian of phi. And therefore, what I see is, from this equality, Laplacian of phi is equal to minus 2 mu alpha, which is actually what I promised you that I would show as well. Laplacian of phi, we know it has to be equal to a constant to satisfy compatibility, but we didn't know what that constant was. That constant is equal to or proportional to the twist per unit length. So if you eventually find what phi is, you can go back and determine what alpha is, or vice versa. If you know alpha, you determine phi, and you can determine afterwards post-process and calculate the torque. All right? We are. And we have completed both solution approaches, the framework for them. And now I'd like to demonstrate, after a short break, how they work on a specific example problem. Okay? Thank you.